Next, we will introduce a whole new concept called an infinite series. So let's get started. In order for us to introduce series, we have to consider a sequence. And sequences is something that we talked in the previous lesson. It's an ordered list of numbers, and it looks like this, more or less. And now if we look into the sum of all of the elements of a sequence, just like that, we're going to add all of them together. This sum is called an infinite series. And usually the word infinite is omitted, so we just call the sum of all elements of a sequence a series. And the sum of all terms of a sequence, believe it or not, can be finite. Of course, it can also be infinite, which is not surprising at all, but it can be finite too. Here's an example. If you consider the sum of all odd numbers, that sum will, of course, be infinite. However, if you consider the sum of all reciprocals of powers of 2, that, surprisingly, will add up to 1. And there is a nice geometric proof of this fact. If you consider a square of size 1 by 1, and then if you take half of this square and add it to 1/4 of that square, so then later you can add 1/5, 1/16, 1/32, and so on. You can see how if you keep going this way, continue the process infinitely many times, you're going to fill in this entire square 1 by 1 with those tiles, but the total area of a square of size 1 by 1 is equal to 1. So again, this is a very, very important observation. This is what makes it interesting to study series. Another example, if you take the reciprocals of, now that we know that reciprocals of numbers get pretty small and can be added together, and the answer can be finite, what if we take the reciprocals of all natural numbers and add them together? Well, the answer will then be infinity. However, this specific sum is so special that it has a name. It's called the harmonic series. So one thing that you need to remember is that the harmonic series, the sum of the harmonic series, or the harmonic series itself, is infinity. So I want to briefly discuss why is it so. Why is harmonic series why is it infinity? And let's take a look at the sum once again. So we have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus, I'm going to go up to 1/16 and so on. And let's group this. Since 1/3 is greater than 1/4, what's going to happen if I replace 1/3 with 1/4? So what if I take this series and I start replacing certain terms with smaller terms? Then I'm going to get a smaller series than the original one. Now, for the same exact reason, what if we take 1/5, 1/6, and 1/7 and replace them with 1/8, since all of them are larger than 1/8? Well, we're still going to we're going to create a smaller series. Now, if we do the same thing with 1/16 and replace 1/9 and all the way up to 1/16 with 1/16, we're going to continue making it even smaller and smaller and smaller. So at the end, do you agree that the the series that we have below is now smaller than the series that we have above? Because we replaced terms with the smaller terms. Now if we do strategic grouping here, what's 1/4 plus 1/4? It's 1/2. What's 1/8 plus 1/8 plus 1/8 plus 1/8? Well, it's 4/8, which is 1/2. And what would be 1/16 plus 1/16? 8 times. It's also going to be 1/2. So if this pattern continues, we're going to end up with basically infinitely many 1/2s. So infinitely many 1/2s will add up to infinity, and you're still going to have an extra 1 here. So since the sum of a smaller series is infinite, that means the sum of the larger series must also be infinite. This is a simple argument to convince you that the harmonic series is infinite. Now we adopt the following vocabulary. If the series has a finite sum, it is called convergent. Otherwise, when it doesn't have a finite sum, it is called divergent. So 4 plus 2 plus 1 plus 1/2 plus 1/4 plus 1/8 and so on is convergent or converges. And the harmonic series, once again, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. We say it diverges. Now we're going to develop some notation here, as it is not convenient to keep writing those infinite sums using the ... notation. So to improve the notation, we're going to recall the big sigma notation. So if we use a big sigma notation like this, that means we're taking the 5th term, adding it to the 6th term, to the 7th, to the 8th, and to the 9th. So in this big sigma notation, this represents the starting index, this represents the ending index. So, and this is called the large sigma notation. So it is very important for us not to lose track of what we're working with. We're going to be working with sequences here, which we denote with curly brackets. And we're also going to be working with series, which we will be denoting with big sigma notation. And we're going to choose some letter for the index. So it could be K, could be I, could be J. And this will express the series associated with that sequence. So again, for example, if we have a sequence AN defined by a formula like this is a sequence. Now for this sequence we can create series like this, and we can use the same letter, but we don't have to, so we can just write the series this way. Now for every sequence there is one series, but for every series there are actually two sequences associated with that. One is the sequence, the terms of which are used to build the series, but also for every series the sum of finitely many terms is called a partial sum, and actually it's not just called the partial sum, it's called the partial nth sum. So it's the sum of first nth terms, and the partial sum can be expressed like this. It is the sum of the first n terms, and using the big sigma notation we can express it like this. So let's get used to this notation. Let's find S4 for the sequence, or let's give it as a series, for the series like this. So what is S4? S4 is the sum of the first four terms and it will be 1 plus 3 plus 5 plus 7. That will be equal to 16. Now if we take all partial sums, and put it all together in the ordered list, then we're going to obtain what's called a sequence of partial sums. And now the following is really important for us to remember. Every series is associated with two sequences. So the first sequence, it's the sequence of the terms. And it can be written like this. And the second sequence is the sequence of the partial sums that can be written like this or equivalently like this. So for example, if we look at the series of made of odd numbers, the first sequence that corresponds to this series is the sequence of the odd numbers. So it is 1, 3, 5, 7, 9, etc. And the second sequence is the sequence of partial sums, which the formula for which we may not know immediately, but we can try to figure it out. Let's write out some of the terms of the partial sum sequence. It will be 1 plus 3, 4, 4 plus 5, 9, 9 plus 7, 16. So again, I'm just adding, like, how do I know the next one is 25? I just added the first 5 terms here. 1 plus 3 plus 5 plus 7 plus 9 is equal to 25. So this is the sequence of partial sums. Now, we don't know what it is. We didn't know what it was originally, but now we can speculate that the partial sums is actually n squared. And what do we know about the sequence of partial sums? We can actually, we are pretty sure that the sequence of partial sums, the limit of that is infinity. And that limit is the reason why this sum is infinite. Notice how the limit of this is also infinity, but that's not the reason why the series is infinite. So again, it's always important to remember the fact that every series has 2 sequences associated. Let's do another example. Let's consider the following series, and the series of partial sums, the sequence of terms is just this. So it will simply be 1/2, 1/4, 1/8, 1/16. So we can see that the limit of this sequence is actually 0. Now, if we consider the sequence of partial sums, we originally don't know what the formula is. It's not an easy question, but we can try to add some of these terms to produce the sequence. So the first term will be 1/2. The next one will be 1/2 plus 1/4, so it's 3/4. The next term will be 3/4 plus 1/8, so it's 7/8, and then it's 15/16. And if you see the pattern, you can actually now figure out the formula. It looks like it will be 2 to the power n minus 1 over 2 to the power n. And now if we look at the limit of this sequence, so what is the limit of 2 to the power n minus 1 over 2 to the power n as n goes to infinity? We can use the very useful theorem from one of the previous lessons and consider the limit of the following function. And at this point we can use L'Hopital's rule or anything else, but it should be pretty easy to show that this limit is equal to 1. And the fact that the limit of a partial sum of a sequence of partial sums is equal to 1 is the reason why the infinite sum, or this infinite series, is equal to 1. So that was a very good observation, and we're going to generalize it. So the sum of a series can be expressed like this. We can take the sequence of partial sums. So basically, we, instead of infinity at the top, we're going to put n. So this represents the nth partial sum. And if we take the limit as n goes to infinity, what are we going to get? We're actually going to get the limit of Sn. And basically, what we learned from the previous two examples, whatever that limit of Sn is, could be infinity, could be some L, it may not exist. That's what we're going to call the limit of the original series. So here's the fact: the series converges when the sequence of partial sums converges. And why is this important? Well, this is important because we just spent quite some time revisiting sequences and their limits, and we said that we pretty much know how to find the limit of any sequence if it exists. Now, when we're about to start learning new objects called series, it is nice that we were able to relate what we're about to learn about the new objects to something that we already knew about the existing objects. In this case, now we know a lot about series because we know a lot about sequences. So the convergence of a series is basically the same as the convergence of a sequence. And the same question, the main question, which will be the same question, is: does the given series converge or diverge? This will be the number one question in this and the following few lessons. Now, let's acknowledge the fact that the answer is pretty straightforward. When the sequence of partial sums is given by a formula, right? Then we basically turn the question about convergence of a series into the question about convergence of a sequence for which the general formula is given, in which case we have the very useful theorem and then the L'Hopital's rule and so on. But this question is not so easy when this formula is not given. And in general, it is really hard to find the formula for Sn. So this is the biggest problem here. We kind of know what we would have done if we had the formula. The problem is that very unlikely that we will be given that formula. However, if we for a second assume that we know that our series converges, the convergent series have some nice properties. All this property can be described with one word, linearity. And that means if we have two series, and now I'm going to use letter n as an index, and let's just for short write our series like this. So if we have two series an and bn that converge to a and b respectively, then the following series made of some linear combination of an and bn also converges, so it's also a series, and we know it converges to the following sum. It's going to be Ka plus Lb, which means that when you have an infinite series like this, you can separate it first. So you can separate the original series into two series, and then you can factor out the constants from a series. So it will look like this. Let's do a quick example. Let's assume that one series converges to 2 and another series converges to -5. And let's find the sum of this series. According to the linearity, we're going to have the following result. So the final answer is 2. So we had a brief introduction to series. We define what it means to converge for a series. And next we will learn special types of series.